Hi, everybody. We're going to look at just-in-time 1.4, 1.5, and 1.8 today. So we'll be starting off with 1.4, and that is looking at exponents or raising something to a power. Okay. An exponent is just a shorthand way of writing when you're multiplying something by itself multiple times. So a to the n would be a times a times a times a n times. Okay. So like a squared is a times a cubed, a times a times a, 3 times. Okay, so a to the n is just n times, and so n could be anything. All right, so some terminology. When we're dealing with exponents, we call a the base. That is the number that's being multiplied. N is our exponent. That's the number of times we're going to multiply the base. And then, as I said, you may have also heard this referred to as raising a number to a power. All right, so some properties of exponents. Okay, you can, if you're multiplying exponents with the same bases, then you can add the exponent. So for example, if I've got a to the n times a to the m, okay, I have the same bases, so both a's, so I'll add my exponent, so it's the same as a to the n plus m. Okay. If I'm dividing by the same basis, then I can subtract the exponents. So if I've got a to the n divided by a to the m, that wasn't an m, okay, then that would be a to the n minus m. All right. Now, these two can only happen if you have the same basis. Okay, so if I'm raising an exponent to another power, then I'll multiply the exponents. So for example, if I've got a to the n, and I want to raise that to the m, then I would just multiply the exponents. So it'd be a to the n times n. Okay. If I'm multiplying bases, then I can distribute the exponent. So if I've got two things, so let's say a so I've got a times b to the n, I can distribute my exponent, and it'd be a to the n times b to the n. Okay, now I can only do this if I'm multiplying. If I was adding, I would not be able to do this. Adding is something different. Okay, I can also do this though if I'm dividing. So multiplying and dividing, you can do this. Adding and subtracting, you cannot. So if I'm dividing, I've got a over b to the n. That's the same as saying a to the n over b to the n. Okay, and then our last is that a negative exponent, then we invert the fraction. So if I've got like 1/2, well, here we're just keep it general. So I've got a to the b to the negative n. That's the same as b over a to the positive n. Okay. If I had something like 2 to the negative n, that's the same as saying 1 over 2 to the positive n. Okay. That's just a special case of that property. Something to remember, I mentioned this, but if you're adding, okay, you cannot distribute the exponent. Cannot. Okay? Or when you're subtracting, same process. You can only do that if you're multiplying or dividing. All right, so there's exponents. So the next thing that we'll talk about that's connected to exponents is roots. Okay, so square roots, for example, I do that every time. Square roots We say that y is the square root of x if y squared is equal to x. So square root is kind of like the inverse function of squaring a number. It's undoing that operation. Okay, so if we look at an example here, we've got 4 times 4, which is the same as saying 4 squared is equal to 16. So 16 is the square root, or so 4 is the square root of 16. Okay, or we've got square root of 16 over 4. But what about negative 4 squared? So negative 4 squared is also, so that's negative 4 times negative 4, which is equal to positive 16 as well. Okay, so if we've got the square root of 16, that can be either positive or negative 4. Okay, and you can stack the exponents like that. Or not the exponents, sorry, the signs. Okay. Now, what about, so that's the square root. Square root, you'll always have the two cases like this, because anytime you square something, that's just how it works. So if I had like 2 squared is 4, negative 2 squared is also 4. Okay, that's a property of square roots. Cube roots, for example, so we say y is a cube root of x if y cubed is equal to x, or if y is equal to the cube root of x. So if we do an example, we're looking at the cube root of 27. So 27 is the same as saying 3 times 3 times 3. Okay, so the cube root of 27 is going to be equal to 3, because there are 3 3's here. Okay. Another example would be 64. 64 is 4 times 4 times 4. So the cube root of 64 is 4. Okay. Now, if I have cube root of negative 27. Okay. If I have negative 3 times negative 3 times negative 3, so negative 3 cubed, that's the same as saying negative 27, or that's equal to negative 27. So the cube root of negative 27 is negative 3. So with cube roots, it's not the same as with the square root. So with the square root, your answer is going to always have a positive and a negative possibility. With cube roots, it will just have whatever answer comes out to be. So if it comes out as it's 3, it'll be 3. If it comes out as negative 3, it'll be negative 3. Okay, so these are 2 examples of what we can extend to higher orders. So if we break it down into 2 cases, if we've got the nth root of x, okay, we've got the nth root of x, there are 2 cases. If n is even, so like a square root, then our answer will always be positive or negative, whatever that nth root is. Okay, now when n is even, we cannot have nth root of some negative. So we cannot do square root of negative 16. Okay, it's not possible. Because there's no number that I can multiply by itself to give me back a negative number. That's just not mathematically possible. Okay, so that's when it's even. Now, when n is odd, then we take our nth root of whatever number we want, and that can be any number. We can have negatives under there like we did with the 27, okay? And there will always be exactly 1 root, okay? This, I know this may seem a little confusing now, but as we do some examples, you'll kind of learn and see and get more comfortable with it. All right, so roots can also be expressed using our exponent notation. And this will be something that we use often in this class, all right? So if we've got the nth root of x, we can rewrite that as x to the 1 over n, okay? Where this n comes from whatever the root is. So if I've got the square root well, my pen stopped working. Give me just a second. I've got the square root of x. I can rewrite that as x to the 1/2 power. Okay. Now we can also raise a square root or raise a root to an exponent. And if that's the case, what happens is, remember, so we can use, we'll rewrite it as a fraction. So it's x to the 1/n to the m. And then we've just got two exponents, and we said in our exponent rules or exponent properties that we just multiply exponents. So that becomes x to the m over n. And this is the property, so this is how roots cancel each other out. So if I had the square root, well, let's do a cubed root of x to the cubed power. Okay, so that becomes x to the 1/3 over, or raised to the 3rd power. It's x to the 3 over 3, which is just 1. So it's just x. Okay, so that's kind of where that canceling out comes from. But that's for any of them that you can do that. They just may not always cancel out. Okay, so all of our laws for exponents, all of them apply for roots as well, because we can write them all as powers. Okay, and just like with our exponents, you cannot distribute over addition or subtraction. Cannot. You can split over multiplication or division, but never addition or subtraction. Okay, so that is our roots and our exponents. And if you've got more questions on those, we'll do some examples in class, and you can always feel free to ask me. Our last section for this video is a little of a different topic. Okay, so we're looking at intervals. So an interval is just some connected piece of a number line. Okay, it can be finite or it can be infinite. Let's look at some examples of finite intervals first. So if we want to include our endpoints, we will use square braces to show when we write it in interval notation. On the number line, we can either use square braces. Okay, so we're going from -2 to +2. Okay. Or you can use closed-in circles. Oh, here. Either method works. They both mean the same thing. So that's for if we're including the endpoints. If we're not including the endpoints, then our interval notation, we use parentheses. Okay, and we can either use parentheses on our number line or open circles. Okay. Something to remember. So the reason why we would use this not including the endpoints notation as opposed to just bumping down to the next whole number is because there is stuff in between there. Okay, so if we are not including the endpoints, it includes everything up to that 1 point though. Okay. We can also split it so we can include one endpoint and not the other. So if we're not including -2 and we're including +2, and we catch everything in the middle, you could use circles as well. So those are finite intervals. We can also have infinite intervals. And so it can be infinite on both ends. And if that's the case, then it's just arrows, and we're including, it's the whole number line goes from +infinity to -infinity. We can give it an upper bound and include one endpoint. So it goes from negative infinity all the way up until positive 2, which gets included. Or we can give it a lower bound. We can also exclude it. So if we're not including negative 2, and then everything above it until positive infinity. Okay, and these two cases can be switched as well. We can not include upper bounds and we can include lower bounds. It just depends. Now, something to remember. Okay, you can include or exclude an endpoint, but you can never include infinity. Okay, so what this means in terms of your notation is that you should never, absolutely never, have a square bracket on the infinite end of an interval. Okay, so if you see here, none of these on the infinity side have a square bracket. Okay, that's because we don't know what infinity, like we know infinity is a concept, it's just not an actual number. And we can only include actual numbers. Okay, so just don't ever put a square bracket there. All right, we can also combine intervals. There's a couple operations we can use. Okay, so we've got, if we've got two intervals, so A and B, if we want to do the intersection of those, okay, that's the set of points that are in both of the intervals. Okay, so the intersection is what's in both of them. It's the and. So it's in A and it's in B. Okay, we use it with an upside down U, or we use an upside down U to write that. Okay, so for example, if we were going to do -4 to 0 and, or intersect with -2 to +2. So we'll do, the easiest way to do this is to draw it out. So we've got -2 included until 0, which is included. And then we've got, if I use red for this other, we've got from -2, which is included, all the way until +2, which is included. All right, and so now our goal is we want to find what's in both of them. So where do those intersect? So it's from -2 to 0, and both endpoints get included. So our intersection of this, that would be the same as saying -2 to 0. All right. Another operation that we can do is called the union. So that's the set of all objects that are in either A, or it's in B, or in both. Okay, so it's in, as long as it's in one of the two, it's good. And we call that the union, and we write it with a U. Okay, so if we did, for example, -4 to -4 to 2, union 0 to 4. So I'll use red for -4 to 2. So -4 all the way up to 2, not including the endpoints. And then if we've got 0 to 4, so 0 to 4, still not including the endpoints. So the union is anything in this, so it's either in A, or it's in B, or it's in both. Okay, so our union is everything from -4 to +4, not including our endpoints. Now, something to look at or think about. So right here, the 0 and +2, they were not included in the original intervals that we used to draw them, but because they were included, so 0, for example, wasn't included in the blue interval, but it was in the red interval. So then it gets counted, and 2 is the same way. Okay. All right, the last thing is not necessarily an operation, but it is a special type of set. And it's a set that contains no elements, and we call that the empty set. And we write it with a 0 and a slash. So for example, if we took the intersection of these two sets or intervals, so if we took -4 to 2 to -2, sorry, and we union that with 0 to 4. Okay, so the union is we're looking for all the elements that are in both. Now there is no overlap here. So that's what we call the empty set. Okay. All right, so that is just-in-time 1.4, 1.5, and 1.8. If you have any questions, let me know, and we will also be talking about this in class.